And I will chair this session with Anders Malthe-Sorenssen. Simple. Please go ahead. Behavior across scales.
Thank you. So I'll try to bring maybe a slightly different perspective. We'll see. So my background is somehow in the border between physics and geoscience. I worked for the last 20 years trying to understand how mechanics and chemical reactions and fluid transport are coupled as a physics problem, but of relevance to processes in the Earth crust. I'm particularly interested in trying to understand how this coupling can accelerate many of the processes in the Earth crust so that they go from being slow, diffusion-driven, boring, to fast, non-equilibrium and exciting. And this is also what I'll discuss a bit today. It's actually not really my first venture, but my first real venture into friction. Actually, in Norway we have quite a large petroleum industry, but we also have, for some strange reason, an industry in producing aluminum, mostly because we have a lot of hydroelectric power. So 15 years ago we had a project where we tried to figure out how to understand what happens when you do aluminum extrusion, which is actually a very interesting problem. There's a lot of very interesting, cool things that happens in this die when you extrude aluminum. We did it for 5 years and we were not able to really help the people who did the aluminum extrusion. They still do it by hand mostly. They have this small die and then they try it once and then something wrong happens. And then some experienced guy picks it up and they polishes a bit. And then they do it again. And this is how they try to produce car parts. For being in competition with the steel industry, so it's not very competitive. But it brought my attention, at least, to this issue of friction. And then I was really introduced to friction, I would say, by a collaboration with Julien when he was a postdoc in Oslo, and then we started a more proper study of friction. And this is part of what I'll be discussing today. So, of course, if you, and you're all familiar with this, but if you want to motivate the study of friction, we could, of course, start from something more industrial, like rear, we discussed in one of the posters discussions there, or you could start from this catastrophic type of phenomena during earthquakes, where of course also the basic understanding of friction is important. I like a slightly different perspective. This is from Trolleslottet, which is the Troll Castle in Antarctica. So this is a 1,500-meter wall. And what I just want to bring your attention to is some of this strange patterning in this wall. All of those strange patterns are due to fractures. And you can zoom in a bit and you can see this little red guy which looks like Santa Claus down there. He's sort of doing the field study in Antarctica, and you can also see some of these large-scale fractures. And you can also see that something has happened around these fractures, which is maybe, who knows, I'm not going to answer that question now, but it might be related to what happened when those fractures were formed. So what happens during the faulting or frictioning process is also maybe conditioning the rock around it for some type of chemical reaction. Actually, there's also a slightly different phenomena in geoscience, which is really fascinating, and that's the formation of something we call cytotachylites, which is essentially the formation of glass due to frictional heating. And you can see this. It's not easy to see this vein here, but this is one large vein, and you can see the displacements of other earthquakes that have been occurring. And each of these small veins here looks like this. If you zoom in, this is 100 micrometers. So this thickness here is maybe a few hundred micrometers. So this is the result. This is like a fossil earthquake. It's what left afterwards when the rock has melted, and then it's very rapidly cooled again. It's quenched, so it becomes a glass. And you can find this, and you can use this to try to understand something about the distribution of earthquakes also in the deep crust. And I'm going to come back to this because this is also an interesting example of what happens when things melt during frictional sliding. But what I really find fascinating about friction is this coupling across the scales, in some sense. What does that mean in this respect? It means that when two surfaces start to slide relative to each other, the motion really starts at the atomic scale, but the motion is macroscopic. So you can't really avoid this problem of figuring out what happens on the smaller scale and what happens on the larger scale at the same time. So friction and fracture are similar in that way. That they really couple, and thereby they also test our understanding of the physics on these across these scales. And this, of course, is a real challenge because friction is really coupling these scales. It's coupling the macro scale behavior through some mesoscopic or intermediate scale where geometry, some of the geometry is important. We start discussing asperated dynamics, down to the really small scale where you have the formation of individual asperities and the ruptures of these, which we are discussing. But my real interest in friction then came essentially as a result of a series of experiments that were performed by J. Feinberg in Israel, which really put the point on some of the issues that at least I didn't really understand at that time. Some of them maybe we understand better now, but that also pointed to some of the unknowns in friction. So I'll go through this experiment in some detail, because what I'm going to do afterwards is to try to see how can we explain the various aspects of this experiment in detail, gradually building up a model going from the continuum scale and adding more and more finer and finer scale processes to explain what happens. So bear with me if you know the details of this experiment, but the idea is that you look at essentially a two-dimensional experiment. I brought a prop. So this is like my two-dimensional experiment. So with a thin plexi plate sliding on some surface. And the idea is that using a very high frequency camera, you can essentially observe the contact area on the surface because of changes in transmittivity. Because when you are in contact, you can transmit, the laser is transmitted through so that you can see the amount of intensity on the other side, reflecting the real contact of the surface. And you can do, and you were able to do this at a really high time resolution so that you can resolve what happens as one of the surfaces starts to slide relative to another. And then there's a lot of details that appears. And you can see some of the details on the macroscopic scale as well. If you start by looking at the loading curve, the force with which you push, as a function of time as you push gradually. You can see some of these small dents in that curve before you start entering this more regular stick-slip regime. And then you can look at how does this image look like. So these are the images as a function of time here and position. And what you can see is that at certain times corresponding to these dips, there is a small displacement in this curve, which essentially shows that there is a small slip occurring on the surface, but it's not all along the surface. It's only for some of the surface is slipping, and as it's slipping, as part of this thing is slipping, that's why it shows something that was soft, you sort of have a small displacement, which is not all along the front. So this is what you can see here, this small displacement that is moving further and further into the surface as you continue pushing. And we call this small displacement precursors. So each of these precursors correspond to some area, and continuously you have some deformation of the whole block. In addition to that, you can characterize quantitatively these precursors. So you can measure, and this was what was done, you can measure the length of the precursor, how far in it reaches, as a function of the force which you push. So eventually, when you reach the static friction threshold for the whole block, that's when this precursor reaches all the way through the surface. This corresponds to your precursor length being equal to the length of your system. In addition to that, you can also measure things like the, I'll come back to that, it's possible they were able to measure the distribution of shear forces on the bottom and the distribution of normal forces, which is essentially then just given by this picture, the transmissivity of the image. But what really was fascinating with this experiment were essentially two results. So if you look at how this front propagates through, when it propagates all the way through, essentially in some cases you have a very particular behavior where it first moves with the sub-Rayleigh wave speed, fast, very fast front, and then it slows down, and then it continues moving fast again, almost to the velocity of sound. And it's almost 1 to 2 orders of magnitude difference in the velocity in the fast phase compared to the slow phase. In addition, you can go in at a point here and you can measure what is the motion of this point as a function of time. And you'll see that what happens is that first it's a fast displacement and then it's a slower displacement before it's more or less is arrested. And it turns out, if you look carefully at this, that this time or the behavior of this slip curve is only dependent on time. It's not really a length dependence, it's a time dependence. Which means that probably what's happening is something with a time scale, something related to melting on that surface. In addition to that, they also measured the velocity of this front, how fast does the front propagate through, as a function of the local stress ratio, and also found a broad range of velocities corresponding to a quite broad range of stress ratios. I'll come somewhat back to that, but I'm not going to discuss the velocities in detail today.
What kind of material was this?
This PMMA. So, faced with this type of problem, my approach would be how do we develop a reasonable model for this type of system? And of course the real system is three-dimensional block on some other block, and with some type of external loading mechanism that ensures a rather uniform load on the top. The first thing that we decided was not to include the third dimension, essentially to make it purely two-dimensional. They weren't really that large. It was experimentally still a quite thin system, and there weren't really that large differences in the orthogonal direction. And then we also simplified the bottom surface. This is something that essentially removed maybe an interesting part of the problem, but we assumed that the bottom surface was infinitely stiff compared to the elastic material that was pushed. This is something we should maybe redefine later. And then we push on it with a spring, and we still load it rather uniformly. And the first attempt then was to say, okay, how can we now subdivide this and start adding physics? So we subdivided it into a one-dimensional model, which is now your traditional 1D spring block chain, where you push with some velocity, you have individual masses and individual normal forces on that block chain. Something, and then you have to decide on some, so this models now the overall elasticity of this whole block. In addition, you need to decide on some type of contact law for the contact. And this is what we're going to now refine. I'm going to start with a simple contact, and then I'm going to gradually refine this and gradually refine the description of the elasticity of the system in addition. So we started with a simple Malthe-Sorenssen law. This has a very unfortunate effect, and that effect is that you introduce a length scale in your system, which is the block size, because you stop all deformation when you are sticking. So it's useful to do essentially what you do in a finite element type approach. You need to regularize that type of interaction by introducing a small elasticity essentially in that law, so that you allow it to deform slightly following this type of behavior until it reaches its maximum, and then it will slide, but when you reattach it, you reattach it again with a spring that can allow it to deform. So introduce a length scale essentially associated with this deformation, which is essential because that means that you'll have a physical length scale, which is related to the interface stiffness instead of a physical length scale, which can be arbitrary, corresponding to your block size. So you'll have a decay, an elastic decay length in your system, which is independent of the block size. So it makes it more amenable to solving it numerically and trusting that type of behavior. So I started to introduce these precursors. So in this case, this is an experiment done by Magawa and was published in 2009. That's also where we started, essentially. This again shows the loading curve, probably from a simulation. This is clearly from a simulation showing the precursors. So these are these small precursors propagating inwards as they gradually increase the push on one side. And then what they did was to vary the loading on the top. So they could either push most on this side, equally distributed, or more on the other side. And what they then found was that this behavior showing how the precursors behaved as a function of the force ratio was changing depending on this type of loading asymmetry. So this is something now we could address directly using this model, because we allowed for having different forces, different normal forces on each of the blocks. So you could do this directly, you could try to model it, and then you can see how does the precursor length in the model vary for three various types of asymmetries in the force distribution on the top surface. And what you can see is that there is something that's looking, there is some type of similarity, but it clearly doesn't reproduce what you see in the experiments. But there is some type of similarity. And let me then also introduce you to one more additional effect, and that is something that we didn't include at all currently in these models, is the effect of the initial stress state, the surface stress state. I mentioned that you could measure this. So in the experiments, you can measure what's the shear stress as a function of position. This shear stress as a function of position. Now we could set up this in the one-dimensional model. We can't really produce it because it's one-dimensional, but we could, given that we know the stress state, we could more or less set up this stress state. And how do we do that? We do it essentially just by changing the positions of all the blocks when we start. You could calculate this using a finite element model, for instance. How would it correspond to a given stress state of your system? And then you can set up the one-dimensional system. And here is set up using three different type of distributions of initial shear stresses. So you can start with something which was flat, which was what I did before, and then you could gradually increase the tilt, which is a very coarse approximation to this more elegant and real shape. But if you do it, you do gain some type of improvement in your prediction for this precursor length. How far does the precursor propagate as a function of the force? So it's looking somewhat more like I didn't really include the experiments here, but here I'm comparing it instead with this PMMA block experiment. So we're approaching something which has this sharp uplift turn near the end of where I reach the front that propagates all through the sample, but it's still not very satisfying. It gives some insight that the initial stress state is important, but it's not very satisfying. Why? Primarily because we are not including any type of real elasticity. It's only this one-dimensional elasticity. There is no real coupling throughout the whole block. So the next step then was to introduce a two-dimensional system. We used a two-dimensional block system. I'll come back to some of the reasons for that. It doesn't really matter whether you use this or some other method for solving the elastic problems. Again, I would prefer at least to use regularization. We didn't really use that in all the problems, but you should still regularize the surface contacts. This simulation in this two-dimensional system, when we load it and then we study either the shear force in the simulation, this is now the shear force, and this is the block number, so this is essentially the position here along this side. This is the initial shear force, and these are essentially showing the normal force, because it's the normal force multiplied by the static and kinematic coefficients of friction. So this is the initial shear force. So if this shear force reaches the static coefficient of friction, I'll induce local sliding. Also, notice that the shape here, which is just due to the loading now, the normal loading of this two-dimensional system, does have similarities to what's measured in the real system. So, or at least we could also set it up so that it depends a bit on exactly how you load the system. There is some history dependence in how you load it. You have to think about the details and how you set up your simulation as well, but you do get something that looks similar. So what happens now when we start pushing this block from the side? What happens is that at some point you'll push and you'll reach, the shear force will reach this static friction threshold, and then it will drop to the dynamic friction threshold, and then this front will now gradually move inwards like this. So this is one front moving inward gradually through the system, either stopping or propagating all the way through the system. As we do this, we can now measure in the model the normal force. So these were the experimental results, and these are now similarly reproduced normal force distributions as a function of the number of precursors. So you start with something that's quite flat, and then you build up this profile as more and more precursors are propagating through. So it's essentially these precursors that's setting up this normalized stress field. And then it's also this is the result after the surface has propagated all the way through, after the front has propagated all the way through the sample, for the case of equal loading. We can now also test this for both for the full set of results, so we can see how does now the model produce the precursor length as a function of this force ratio, and we can compare it to the experiments directly, and we can also do this for these unequally loaded systems. So our conclusions based on this is that yes, indeed, much of the properties of these precursors, which are essentially static properties of the contact, we can understand more or less only from two-dimensional elasticity. There isn't really much more in that. But you need the two-dimensional elasticity to gain a reasonable understanding. But then there were these two other effects. It was this slow slip thing, and it was the slow fronts. Where does that come from? Well, if you want to model that, we might have to refine the way that we model the friction law. Currently, the friction law was the Malthe-Sorenssen. Well, I'd like to refine it so that I put more physics into that friction law. So I still have this is my macroscopic block, and then I zoom in on one of these, then I have some type of elastodynamic, maybe an effective friction law region on the mesoscale. But now I also would like to introduce the single contacts. So far, this is essentially what I've done. I started with this macroscale, I introduced this mesoscale with now an Malthe-Sorenssen law on this scale. What I'd like now is to add a new level to this description, having some description that includes something like asperities. And what we essentially then shows was inspired by a model that had appeared just a few years before by Brown et al., where they modeled each of these blocks as being in contact with the surface through several asperities. And those asperities, each of them, have some type of simple law. I'll come back to the details in that law. This also introduces, not quite nicely, sort of the difference between an elastic screening length in the sense of each of these blocks having a separate size, essentially, which is non-elastic, and then is elastic on lengths larger than that. And then introduce the elasticity of each of the asperities through each of these bonds. So that's the idea. You can motivate this from sort of several types of motivations. It can be in the form of single microcontacts. It can be this solid pin island type model of melting regions, or it could be a single molecule representing each of these bonds. I'll admit something, and that's the model we chose was chosen more by accident than by maybe by luck in some sense than by pure understanding initially, but it introduces some aspects of the dynamics which turns out to be crucial to understand what happens. So sometimes these things happen by accident, more or less. So how do you now describe each of these bonds corresponding to one such asperity? The idea is that we describe each of them now similar to this Amundsen-Coulomb type behavior. So it's like one of these asperities and you pull until you reach some type of threshold, the strength. And then after that you're in some type of sliding behavior. We call this one the pin behavior and this one the slipping behavior. And then essentially inspired by the experimental observations that there was a time until it reattached. We introduced a slipping time until it reattached. The slipping time which we chose to be random with some Gaussian distribution. And the number here was chosen so that it corresponded reasonably well to what you found in experiments. So what does that mean? It means that the state here now, the microscopic state, is really described by all of the states of each of these asperities. So, and each of these microjunctions, they can actually have different histories. What's happened, because it depends on what's happened before. So if I want to describe it, I would really like to describe it by, for instance, a distributed of pin bonds. How many of the bonds are really pulled far, and how many of them aren't pulled at all. So you could model it either like that, or as how far are they from their critical distance. So as things are pulled past the critical distance, then they're starting to slip. Then they enter a different distribution, which is sort of the distribution of slipping bonds. And when they have been slipping for some time, then they re-enter as pin bonds. So if you want to learn more of this, there is more of this on Kjetil's poster, I think, describing this. We can introduce this as a very nice conceptual way of describing the behavior, and you can also introduce a nice type of master equation to describe the dynamics of these distributions of pin and slipping bonds. But the underlying idea is that you describe the microscopic behavior by the distribution of all the stresses in each of these bonds, or how long time it's been since they started to slip. So this is now the microscopic description. Then you have the elastic description on the medium scale, and then you have the overall description on the large scale. So based on this description here, you can measure what happens with one block, or you can measure what happens with a whole block as you start pushing it. You can also mention that if you look at the effective friction behavior of one of these blocks, the collective mesoscopic friction law is essentially a monotonically velocity weakening law for each of these blocks with this type of description. Now there is one small detail that I didn't really mention in this law, which turns out to be very crucial. And that is what we did, was that after, when it was reattached, so it's slipping at this level, it was reattached, we set the force to 0. So it reattached, unstressed essentially. And this very small detail in the model formulation turns out to be essential in developing the understanding of why you have these slow fronts. So let's see just what happens. If you now run this simulation model again, we push gradually, we have some normal force. We have this elastic block, it's on the infinitely stiff slider, and now at each of these small points we have this now complicated description of all the slip states of all of these blocks. So if attached bonds are 0, it means that all of them are slipping. So if all of them are in a slipping state, it's like the whole thing is slipping. If all of them are attached, then it's pure elastic deformation. It's just deforming elastically with all the connections with this surface coupling elasticity. So here essentially everything is connected, and then starting from the left side you can see that there is a region here where everything is essentially disconnected. The fraction of pin springs is 0, and it propagates all the way through. So this is what we call this the front propagating through the sample. It's rather steep, so it means that it's rather fast. And you can also see essentially here this reattachment dynamics, which is the time it takes until the bonds are reattached, which is these 2 microseconds on average with some distribution, which is what we put in. There might be some initial disorder here as well. So this is one of the fast events corresponding to the fast. You can also see, examine the same thing for one of these small precursors. What you see then is a similar behavior, but it stops at some point. It doesn't propagate all the way through, and still it takes some time until it reattaches. And this time again corresponds approximately to these 2 nanoseconds. But sometimes, if you run this exactly the simulation, you do get an event like this, event 1. And event 1, without any tuning at all, naturally produces this transition from fast, slow to fast. And if you measure now the velocity, you'll see that this fast event corresponds to the blue guys here, versus this fast, slow, fast correspond to the red, which is rather similar to what you saw in the experiments. You can even see this, the reflection here of the sound wave. You can see the same reflection of the sound wave here. You can see some of the reflection of the sound wave there as well. And it comes back not that clear in this picture. So you see the fast, slow, fast behavior, and we can see the slow, fast, slow behavior. So now the question is, we can observe it in this model that has all of these scales. It's not this rather complicated scale or state at the microscopic scale, and then coarser and coarser at coarser and coarser scales. It's easier to understand what happens, but what really happens on the micro scale. In addition to this, by just measuring it, we can also measure the local slip. What was that? The local slip is how does this move as the front is propagating through. How does one small position move as a function of time? We see in the model that we have similar things. We have a fast slip and then a slow slip afterwards. Similar to what we see in the experiment, where you have a fast slip and then a slow slip region. Here there is another full sliding because we are pushing the system faster than what you do experimentally, because we can't wait too long in the simulations, then it takes too long time. Then we can understand what is the mechanism causing this slow slip in the simulations. So we can see that we get either this slow slip with a full sliding or slow slip where it arrests, right, for a system that stops completely. So what is causing this? What's causing this is essentially the behavioral dynamics of these small springs or asperities. So here we just illustrate what happens as one of the springs are breaking and it's reattaching. So it's breaking and then it's more or less balanced. It's breaking at the force balance, so the external forces and the forces from the surface is approximately the same, but as it slips, we are reducing the force because we're setting this one to 0, and that means that the whole surface is now going to slide slightly forwards. So setting each of these asperities to 0 induces a very slow motion inside, a slow slipping motion inside the system. This sort of happened by accident, but it turns out to be essential. We can also understand now what the origin of this slow slip is in the model. Because we could measure the slow slip, and then we can say, well, according to this, it must depend on the time scale for reattachment. And that is indeed true, because if you make that time scale smaller, then the slip becomes faster. So it progresses further in small time. Or if you make the slip time longer, then the slip becomes slower. So slip is related to this internal time scale, which is related to the slow motion. And we can even study this completely by looking at the slow slip speed as a function of this time scale, and indeed we see that there is a solid scaling, so that it is this internal time scale that's determining the slow slip speed. Indeed, we can also see that slow slip now is actually the process that enables this slow front propagation. How can we do that? Well, we can do this by essentially now turning off this mechanism. We have now a mechanism built into our model, because we allow the systems to relax to 0 instead of just relaxing to the dynamic coefficient of friction. But if we change the model so that instead, in this case, it relaxed to 0, and that means that we had some slow slip, it's moving slowly in this zone here, it's moving slowly all the time. Whereas in this zone here, we turn it off, it's not moving slowly. So what happens, we take exactly the same simulation, we restart it, but we turn off this mechanism, and then we get a result which has the same initial behavior, but it stops. So what's actually ends up being a slow front, in this model at least, is a precursor that is continuing to move due to the slow slip. So it's being pushed from behind, because this whole region here, when it's slipping slowly, building up the stress at the tip, eventually moving the tip slightly forward, continuing to slip slowly, building up the tip, moving it slightly forward. So a slow front is essentially in this fronted wood arrest, but it's pushed forward by this slow slipping. We tested this also by including only this effect in a model. So we made a model which is without all the details. We essentially just replaced all of this complicated state with all of these micro springs with just one single spring. With that single spring, we allowed it to relax slowly, so it had a slow slip. In this case, we got exactly the same, or we get a similar response in the sense that we get a fast response and then a slow response. So we can see the same behavior in an Amundsen's column type law, but where we add the slow slip component. And then we can also understand how does this slow slip speed determine the slow front speed. Now to do that we need to make systematic studies of how the front propagates through the system, and we do that by rigging the system. So we make the system, like I said initially, with a very specific stress profile. So we set it up with a specific stress profile. So this now is giving the stress, horizontal stress, as a function of position along the surface. And we can rig it. So this is the slip dynamic coefficient of friction. This is the static coefficient of friction. This is where it starts to slide. And then what we do, we trigger it by stressing it higher than the dynamic region, and then we sever all the bonds in some small region. So it's loaded, it's stressed, and then we say that all of the bonds in this region, they are cut, meaning that you lose all the contacts. We're essentially just saying that now you are suddenly in the dynamic state. We do this in one region, and then we see how the front propagates in that case. So this is what we can then do. We can then do this, and we can measure in the system the slip speed as a function of the rupture speed as a function of the slow slip speed. And we can vary the slow slip speed by, for instance, varying this relaxation time. Now if we do this, we see that we have a slow rupture speed, which is a function of the slow slip speed. And actually we even developed a theory for it. I'm not going to go through that here, which essentially relates the slow slip speed to relate the slow front speed to the slow slip speed with a constant of proportionality, which depends on essentially the elastic energy. This is the strength of the springs, and this is the length scale, which is associated with the decay of the elastic field close to the tip of the fracture. And then this is how the difference between the threshold and the zero loading. The zero loading was what I introduced here, the initial loading here in this case. So that basically means that we have a good understanding for how this slow slip speed determines the slow front speed. And again, it was sort of discovered by accident in some sense. We put in this slow slip by accident. But then afterwards we can see that it really is important in order to get the right type of dynamics. It doesn't really affect what happens in fast dynamics. I'm not going to look at that in detail now, but we can also study what happens for all the fast fronts. It doesn't really affect them, but it affects what happens in the slow fronts. Let's look at some other properties now of this state, because this is now the idea. We have now a system where we can describe the friction all the way from the states of these small asperities and to the macroscopic motion of the whole system. So what we now can look at in detail is how can we change one front, which is essentially a slow front, is a slow fast front, to being only a fast front. Well, we can do that by modifying the distribution of, essentially we can modify this state of all of these asperities. How can we do that? Well, it's done essentially through the realization that the strength, this effective static friction coefficient, which I plotted here, as a function of the width of the distribution of all the asperities. So I can put all asperities have the same, essentially are in the same state. It's like all asperities are are like this. When I pull, all of them are pulled the same. And this first one, all of them are stretched to the threshold, I'm able to get rupture. That will generate a very high coefficient of friction. Versus if they are distributed randomly along like this, when I pull, then I'm going to quite soon start rupturing some of them. And then I'm just by democracy essentially. The rest of them are going to support all the load, and I'm going to have some type of feedback effect, which means that I'll have an effective weaker surface. So the distribution, the width of the distribution. So here I plot the width of the distribution is the probability, and this is a very wide distribution. This is a very narrow distribution. A very wide distribution gives me a low effective friction. A very spiked distribution gives me a high strength of the surface, like the coefficient of static friction. So now what I can do here is that I can make the surface here, make the region here, I can modify it. So this now gives the distribution. It's somewhat complicated. This is essentially telling me the states of all of this micro asperities. But I can modify it by making it wider in this case. Modify it uniformly across the whole range. What does that mean? It means that I make it weaker. If I make it weaker, this front which did stop here is not going to stop because it's weaker. It's going to propagate all the way through. So we can sort of modify it, do experiments by modifying the microscopic scale, and then we can see what are the macroscopic consequences of that modification. And we can do the opposite. We can take one front which is initially fast, and then we can modify a small region here and make it quite strong. And then as it reaches this state, it reaches this position, it's going to stop and then continue as a slow front instead. So we can use this now to characterize the whole system in terms of make a front type phase diagram, where we can see whether we get fast fronts, slow fronts, or a front that doesn't propagate all the way through. Depends on this width of the distribution. So if the distribution is very narrow, then I will typically get something that's arresting, because I get a very strong interface, unless I have a really high pre-stress. Whereas if I have a broad distribution, so that it's weak, then it's easier to get a fast one. So this is the particular behavior we got in this model. This depends on the details of the model. So it's not universal, this type of curve, but we've tried many different models for the microscopic dynamics, and in all these cases we do get something which has the same qualitative features. It's a fast region, it's an arresting region, and the slow region is in between the two. But it can be quite narrow in reality, so it can be very difficult to find it, because it can be very small range in space. Let me not tell. So finally, what actually determines this local strength? Because what happened here was that this naturally happened. We didn't fine-tune it in the first simulation. It just occurred naturally. What is really determines the local strength? What is this? What determines this distribution of force of stretchings? It's the history. It's what's happened before that determines that. And you can look at two simple cases. One case is what happens if it stops really fast. What does that mean? It means that if I look at sort of a rupture, and then I go, and then it stops, and then I go one step back, and that step back corresponds to the maximum length I can stretch one of these asperities. So here I start. So this is sort of the maximum length I can stretch them. So I start here. I move quite rapidly, this length, so that all of them break, and then I stop, and then all of them are essentially attached at the same time. So this is a very rapid stop. A very rapid stop generates a very uniform distribution, generates a very strong, very high coefficient of friction. Versus if it moves gradually all the time, what will happen is that some of them will be stretched, will be sliding, and then they will reattach, and then I'll end up with a quite disordered set of springs, which gives me a broad distribution. So how it stops determines the strength of the interface afterwards in this model, and you can study this systematically by looking at various types of accelerations. Essentially something that stops very fast, so this is the position compared to the maximum position it takes to brake as a function of this relative time scale. This is the reattachment time. So if it stops very fast, this corresponds to this case here. Whereas if it moves all the time, this corresponds to this case. We can measure in the model the effective coefficient of friction afterwards and see indeed we do see a variation here of almost a factor of 5 in this rescaled version. In the real version, almost a factor over 2 in the coefficient of static friction, depending on how the history is. And just for comparison, if you look at the effect of aging, the typical effect of aging is maybe a 20% increase. So this, at least in this model, it indicates that this effect of history can be a significant effect on the coefficient of static friction. Yeah, we've also discussed slightly how we can measure it, but I think I'll actually now move towards summarizing. So what I wanted to illustrate to you essentially is our adventure trying to model in detail what happens in this macroscopic system by gradually increasing the degree or the amounts of freedom we have for describing the asperity distribution. We started by just describing it using a Malthe-Sorenssen with the regularization. We saw that we needed to have the two-dimensional elastic field in order to reproduce static features, like how far does these precursors propagate as a function of applied stress. But in order to see more of the details of the experiments, for instance, to see this local behavior where you first have fast slip and then slow slip, or this transition from fast to slow to fast fronts as you propagate through the system, we needed to have a more complex type of dynamics. Actually, the only thing we needed to add was some type of slow slip. If you add some type of slow slip, then you'll get, or you might be able to reproduce this type of behavior. And then we also had a microscopic model which naturally reproduced this slow slip, which is interesting because that allows us to ask questions like, how does this system that has this slow slip mechanics built into itself, how does this actually set up the coefficient of friction? It allows us to address this question of how does the history, the acceleration, the speed at which you stop, determine the coefficient of friction for the next event. Which I think sort of is an interesting perspective. You can't only look at the state starting from the slip. You actually have to look at the history before the slip in order to determine the initial state value. And at least in this model, it indicates that this modification can be really important. It can be almost a factor of 2 of the coefficient of friction. Now it remains to be seen to what degree this also corresponds to what you see in experiments. Let me then just also point to in what areas this might be important, and then these are some of the areas that we are working on. A natural area where things are melting is, of course, glaciers. Underneath glaciers, this turns out to be a really interesting area as well, understanding the frictional behavior of glaciers. This is what Kjetil is currently doing his postdoc on, is on trying to understand the intermittent behavior on glaciers based on a macroscopic, or based on a law, an improved law for rate and state friction that's valid also for this type of melting systems. It's also important in many tight rocks. Maybe you don't care what tight rocks are, but tight rocks are quite important because they are essentially containing all unconventional hydrocarbons. They are shales or they're carbonates. In Norway, we are producing oil from carbonates. Initial permeabilities. And in these systems, slow slip is essentially what determines the effective mechanical behavior, how they deform, and also which again determines the properties of the hydrocarbon place. And in addition, I think this is sort of also might be very important in order to understand what I started with, these pseudotachylites, these glassy dynamics, these fossil earthquakes, where you can see that the system has melted, because you can see melting structure on the microscopic scale. I haven't shown that here. How can you understand how strength again then builds up in these systems? Well, we might understand how strength builds up, and how strength is, and how strain or energy is distributed between fast slips and slow slips if we have reasonable models also for how this slow slip part behaves, which is sort of one of the outstanding questions, I would say, in geoscience, is understanding this division between slow slip and fast slip in earthquakes. Thanks.
I think we can take a few questions.